Okay, this is the review for nuclear chemistry. Forgive my sick voice, but all right, we're going to start with nuclear equations. A nuclear equation, everything's written in isotopic notation. Okay, that means they're written as nuclei or they're written as isotopes. The top numbers are still the mass numbers. The bottom numbers are the charge or the atomic number. Okay, so an example of a nuclear equation is 226 over 88. This is a very common one. Okay, this is the alpha decay of radium. How do I know it's alpha decay? Because it's natural decay. What does that mean? That means there's only one reactant, and one of the products is an alpha particle. That is an alpha particle. How do you know it's an alpha particle? Look it up on table O. This is a very, very reference table heavy unit, so make sure you use your reference table. Okay? Make sure you notice the mass and charge are conserved on both sides here. Okay, 226 is the mass number. This is my mass number on top. 226 is the total mass on the left. 222 plus 4 is 226. It's the total mass on the right. Okay, the atomic number is the number on the bottom, or the charge. It's also the nuclear charge, so it's the charge of these nuclei. So 88 equals 2 plus 86 on the bottom. If I did not know what this middle thing was, and I wrote it like this, and I said solve for x, solve for that blank, what's in that blank? I would say 226, which is the mass number from the left, equals, the arrow means equals, x plus 222, and I would get that x equals 4, and then I would get 88 equals x plus 2 from plus 86, and I would get that x on the bottom equals 2. So I know it's 4 over 2, but how do I tell what the symbol is? To identify the symbol, you only look at the bottom number, okay? This IDs the symbol. The top number does not, okay? The atomic number is what identifies the symbol. First place to look is your periodic table. Match the number to the symbol on the periodic table. If there is not one that matches on the periodic table, say you have a beta particle, and it's like this, okay? Then you look at table O. Table O are all your other types of particles that you need to know. I'd look at my periodic table. I'd see it's helium. Helium's number 2, and I would fill in the blank. Okay, that's how you can solve for these. If you are asked to write an equation for the alpha decay, or let's say the beta decay of any sort of nuclei, what you would do is you might need to look at table N to see what type of decay it is, because table N has a decay mode. Or you could just write the one that they have. So let's say carbon 6. I'd look up on table N and see that carbon 6 decays by beta decay. So I write the nuclei that's decaying, and then I write my arrow. And then I write the particle that it spits out. Since it's beta decay, it loses an electron. And then I solve for what's left. I say that 14 plus 0, nope, excuse me. 14 equals 0 plus x. So x on top here is 14. And on the bottom, 6 equals negative 1 plus x. And x on the bottom is 7. So that, if I look it up on my periodic table, I see that that is nitrogen. These are all natural transmutations, okay? An artificial transmutation would have 2 reactants, okay? It would be something like, let's say aluminum gets hit with a neutron and turns into an alpha particle, and 24 over 11, and sodium. Okay, that's not alpha decay, that is actually artificial transmutation because of that plus sign. Okay, those are types of nuclear equations. Again, notice the top numbers are the same on both sides and the bottom numbers are the same on both sides. Types of decay, there are 3 main types of decay. There's alpha, there's beta, and there's gamma. There is beta positive, okay, that's a positron. That's got a positive charge, but it's similar to beta decay. When it comes to penetrating power, here we go. penetrating power increases in that direction. That means alpha is the weakest and gamma is the strongest. Okay? Alpha has an alpha particle looks like this. It's a helium nucleus. It has a charge of +2 and it has a mass of 4. A beta particle looks like this. It has no mass and it has a charge of -1. A positron is a positive beta particle. It's the same thing except its charge is +1. And gamma is 0 and 0. Okay, gamma looks kind of like a wave. Gamma is just energy. There's no mass and no charge. Okay. Those are your different types of decay. These are all natural decay. Okay, these are all natural decay. That means they are the only reactant, and then these particles are what may be released from them. Okay, if you're asked what happens to the element, what happens to the atomic number, what happens to the mass number of the element when it undergoes alpha or beta decay, write out an equation. Okay, even if you make it up, but write out to pick a nuclide that undergoes alpha decay. Write out the equation for it doing alpha decay and then see what happens to the mass number and the atomic number. That will make it the easiest for you. Fission and fusion are two types of artificial decay. Okay, so if we're looking at decay, we have natural, which is alpha, beta plus, beta negative, and gamma, and we have artificial. Okay, artificial can be fission, fusion, and all other. Miscellaneous. Okay, so the equation I gave you 2 slides ago, this right here, this is miscellaneous. Okay, this is all other forms of natural transmutation. Artificial transmutation. It's not clearly fission, it's not clearly fusion. Fission is division, okay? When I say that, I mean that you take a big nuclei and you split it by hitting it with a alpha particle or a neutron. It's usually a neutron, okay? So I start with something like uranium-235, and I hit it with a neutron, okay? It's going to be uranium. This is fission, okay? It's going to be uranium or plutonium, but it's usually uranium. And then it's going to split, okay? It's going to split into 2 lighter particles. So it might be, let's see if I have one handy. It might be krypton 92 and barium 141, okay, and 3 neutrons, okay. It's going to be 2 to 4 neutrons that come out. It's going to split into 2 middleweight, not super heavy, but 2 middleweight daughter nuclei. And that is fission. It's dividing, okay? You're starting with 1 nucleus and it's splitting into 2. Fusion, on the other hand, only involves 2 elements, okay? The only elements in nuclear fusion are going to be hydrogen and helium. This is an example. Okay? That's an example of nuclear fusion. You may have a extraneous neutron or proton, so it could look like this. Okay? But the only elements are hydrogen and helium. If you have a hydrogen and a helium, but you have a lithium and a barium or a beryllium or some other element, It's not nuclear fusion. Nuclear fusion only includes those two elements, and it takes light nuclei, like hydrogens, and puts them together, so it combines light nuclei to form heavier ones. Okay, that is nuclear fusion. Okay, half-life. When you do a half-life problem, you need to start with 3 columns. Half-life, time, and amount. You won't always need all 3 columns, but start with these 3. Every half-life, the amount that you have is cut in half, okay? The first 2 start with 0. These are your initial conditions, okay? Your amount is either given to you from the problem, or if it's asking you for a fraction, it's 1, okay? If it gives it to you in the problem, it's not going to be a mass number, okay? So if I'm asking you about I-131, that number, this 131, is not the amount, okay? Not at all. Do not do that. Minus a billion points, okay? If they give you an amount, it'll be in grams. It'll be like 200 grams or 100 grams. So let's start with 100 grams. For this example. If I want to know what's left after 20 days in my half-life, so after 20 days, my half-life is 5 days. How much is left with an initial 100-gram sample? Well, I don't know how many half-lives I'm going through, so just number this down, maybe through 6. 5, 6, okay? And then in the time column, it's very important that you don't just keep doubling it. You need to just continue to add the half-life. So this is going to be 5, 10. My next number is not 20. Okay, my next number is 15. I just keep adding the half-life time in that column to go down. Okay, 20. And 20 matches this, so I'm done. It took me 4 half-lives. Well, how much is left after 4 half-lives? In my amount column, to go down, I divide it by 2. That means to go up, if I know how much I have after 20 days and I want to know what I started with, to go up, I have to multiply by 2. Okay? In this case, I know what I initially started with. So after 1 half-life, I have 50 left. 2, I have 25. 3, I have 12.5, and 4, I have 6.25 grams, okay? If the problem said you initially have 1 gram after 20 days, how much did you start with? You just multiply it by 2 on the way up. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. Make sure you include these initial conditions. I have 8 after 1 half-life. So what did I start with? I started with 16. Okay? That's how you can pretty much do any half-life problem. Make sure you fill out the chart and see how to properly fill it in. Okay? Make sure you read the problem accordingly. Finally, applications. You have to memorize these. Okay? Carbon 14 is for living things or organic things. It's for dating how old living things are. Okay, how long ago it was living. Uranium 238 and lead 206 are for rocks and minerals. Okay, or geologic formations. They have a really long half-life, so there's still some of that sticking around. Iodine 131, super common. That's for thyroid. Cobalt 60 is for treating cancer. Okay? Cobalt 60 is what they do for radiation therapy, what they use. Phosphorus 31 is a chemical tracer. And technetium 99 is used for scans or medical scans. If something's used for a medical purpose, It's got to have a relatively short half-life because you don't want it left in your body radioactive for a really long time. You want it to decay very quickly. Um, except for this cobalt 60, because the radiation therapy, they're not actually injecting it into you. So if it's a medical purpose that's actually going to the human body, like a chemical tracer or this technetium 99, you want it to have a relatively short half-life so it doesn't stick around in your tissues as radioactive for quite some time. You want it to decay quickly. Those are the major ones that you need to know. I would suggest this one, these top four are the main ones that you need to know. So especially these two. Okay? Good luck. Email me if you have questions.